Well, hi, my name is Grant Wilson. I'm a professor here at Umass Amherst, and I'm very interested in studying the evolution of how stars are formed in our galaxy and in our universe. So all the way back from the first galaxies after the Big Bang, all the way to the present day, and how our Milky Way galaxy is forming stars each year. This is my area of research. To do that, I use millimeter wavelength astronomy and make new observations of the sky using the Large Millimeter Telescope, which is a telescope I've been working with and on for about 17 years now. It's located on a mountaintop in Mexico at high altitude, about 15,000 feet. And each night we train our cameras, including cameras I've built here at UMass, on the heavens, where we search for dusty galaxies and various forms of obscured star formation. Unlike in other wavebands in astronomy, where the further away you put an object, the dimmer it is, at millimeter wavelengths, bright dusty sources actually stay bright even when they're all the way across the universe. So we can make images of the sky right now with a camera called Aztec that we built here at UMass, where in the image we see galaxies that are both nearby in the universe and at the same brightness all the way across to the other side of the universe around when the very first galaxy is formed. And they all appear in the same image at the same brightness. And that is a disadvantage because we can't tell how far something away is away, but it's a big advantage in the sense that no one else can see these galaxies at all, or at least a large majority of them. And galaxies that even the Hubble Space Telescope is completely blind to, we can image with our Large Millimeter Telescope and see, and they're in some cases the brightest galaxies in our image. So this is all because big balls of dust have a brightness that is independent of how far away that ball of dust is from us. Now, based on those ideas, we actually first got funding to build the Large Millimeter Telescope, and more recently we've gotten funding to build a camera called Toltec, which is one of the larger millimeter wavelength cameras that will have ever existed by the time we're done building it. So Toltec is a National Science Foundation funded camera that is replacing a camera called Aztec that we built before. Aztec had about 100 detectors in it. Since we built Aztec about 15 years ago, we've learned how to multiplex detectors and make far larger systems. So Toltec will have a whopping 7,000 detectors in it, and also observe in 3 different wavelength bands simultaneously. Okay, so what we're after in our research is to build new instrumentation that gives us a new view of how galaxies get their stars. We look out in the Milky Way, and we know the Milky Way has about 200 billion stars. And the Milky Way has been around for a long, long time in the history of the universe. We'd like to know how this all came to be. We look at nearby galaxies, we see the same thing, billions to hundreds of billions of stars. When did those galaxies get their stars? What were the processes by which gas in the galaxy actually got transformed into stars? With Toltec and the LMT, we can actually go back and look at different galaxies going further and further back in time through the universe's history and start to address how did that star formation take place. And then by extrapolation, we can talk about how star formation will or won't happen off into the future. One of the challenges of doing astronomy in general is the atmosphere above us. And in particular at millimeter wavelengths, our enemy is water. So our telescopes, if you ask about all millimeter wavelength telescopes on Earth, you will find them either at very high altitudes or in deserts. In our case, we're at very high altitudes. Our Large Millimeter Telescope is on a mountaintop at 15,000 feet elevation, but still the residual water in the atmosphere, everything above the telescope, provides a competing signal to the galaxies that we're trying to see that is about 1,000 times brighter than the galaxies themselves. It's painful. So we plan with Toltec, which will produce about 1 terabyte of data each night that it observes. we plan to install a large high-performance computational system at the MGHPCC so that we can run that data through a clustered computer in order to do the atmospheric subtraction and then build the maps of the sky. This is hard because the signal, like I said, is about 1,000 times brighter than anything we're trying to look at. This involves advanced computational techniques, principal component analysis, a lot of Monte Carlo Markov chain analyses, and it's an enormous data throughput at the same time. And so it's a difficult computational challenge, but we've done it at smaller scales before, and we think we know how to scale it up. And with the power of the computational system we'll have at the MGHPCC, we expect to be just fine.